Today we're going to be talking about estimation and inference of simultaneous equation models. And let me see if having it in table mode helps. So estimation and inference in simultaneous equation models. Okay, so as a summary of the previous class, the previous class we defined simultaneous equation models. So remember, this is part of the systems of equations. So simultaneous equation models, we have a system of equations related through the errors and we say that the other thing that we have in simultaneous equation models and some of the dependent variables, in some equations. Well, let me see, and be the dependent variables in some equations are explanatory variables in others. Okay, so that's kind of like the key definition for simultaneous equation models. Then the next thing that we talked about was the difference between structural and reduced form models. Yeah, and once we define that, then we talk about the problem of identification. Which basically tries to answer the question if we can really estimate all of the coefficients of our structural equations. And usually, what is used in practice, to see if our parameters are identified or not, are what's called the order condition. Okay, so that's kind of a summary of the things that we discussed in the previous class. So, the starting point of the class today is going to be these structural and reduced form models. Just a reminder, I'm going to go to the handout that I gave you. So remember, we use this example of demand and supply model, where for the same individual, remember here the index I refers to an individual I. So we have the demand and supply equation, and we have the structural model. So, you should be able to understand how is that we go about writing this structural model. But basically from this example, I show you that this equation represents the structural model. So we have yi tilde hat. So those are the endogenous variables. In xi, we have the exogenous variables. And this gamma is the coefficient related to the endogenous variables, and these B metrics are the coefficients related to the exogenous variables. And then we have the error term. So again, this is a vector of errors where we have the errors for both of equations for the same individual. So remember here, I coefficient represents an individual. So here, the way that we wrote this thing is having in mind an individual observation. And then we said, going from the structural model, once we have written the model in this way, it's very easy to write a reduced form model, and basically what we do is we solve for yi. Okay, so this is what's called the reduced form model. So we have all of our endogenous variables on the left and all of the explanatory variables in the right. Okay, just a reminder. So let me see. So let's go back to the notes we had. Let me save this. Oops, what's going on here? It's not letting me. Where is saving? So okay. So again, let's go back to that equation that we have, the structural model that we wrote in terms of the y and the x's. And this is equal to the vector of error terms. Okay, and we already saw the math. And we said that to go to the reduced form model, this is the way that we write that model. And we also have a vector of errors. Okay, so let's see what are the assumptions that are needed for estimation. So the first assumption has to do with exogeneity. So basically here what we're saying is that those error models in the structural model are uncorrelated to the exogenous variables. Okay, so this is exogeneity of the exogenous variables. Okay, otherwise, I mean, we will be in trouble. And then the other two assumptions are basically the SUR assumptions. So this is a matrix M by M, and I'll talk about that in a second. Let me write down the assumptions, but we already talked about these assumptions in the context of SUR. So these two assumptions are basically the SUR assumptions. Okay, again, so remember that what we have here, and I show you that above. So remember what we have in these metrics, what we have are the errors for the same individual in two different equations. So remember that's the example that we have for the supply and demand equation. So basically what this first condition is telling us is that the errors for the same individual are correlated across equations. Okay, which again, remember that is the SUR assumption. And this second condition is telling us that the errors for different individuals are uncorrelated within the same equation and also across equations. Okay, so basically the way that we're written here is the SUR assumption. So two basic assumptions: we have exogeneity, and the other one is that we have, in this system of equations for the simultaneous equation models, we have the SUR assumptions. Okay, so those are the things that are good to have in mind. Okay, so now let's talk about estimation. And we're going to be talking about estimation for each single equation and also estimation for the system as a whole. So let's start with single equation estimation and inference. Estimation and inference. Oops, this thing jumped on me. And I don't know what is this thing here. Oops, I don't know what I touch. Okay, so that disappear. So single equation estimation and inference. So something that's going to happen here is that we're going to have to switch the notation. And I know that that kind of sometimes confuses students, but I wish we had like a consistent notation. But I'm following the book, and to be consistent with the notation that is used with in the book, I'm using the same type of notation. But we will define anything. I think as long as we define things, when we start to use them, we will be fine. So basically, within simultaneous equation models, we use certain notation for the definition of a structural and reduced form models, but now for estimation, we're going to be using a slightly different notation. And I'll define each term here. I mean, the change of notation is not that drastic, but there is some change in notation. Okay, so what do we have here? I mean, what is that we're writing here? So remember, here we're considering one of the equations in the simultaneous equation model. So yj is going to be the dependent variable, in equation j. Xj is going to be the set of exogenous explanatory variables in equation j. The set of exogenous explanatory variables in equation j. Yj, on the other hand, is going to be the set of endogenous explanatory variables in equation j. So this is going to be the set of endogenous explanatory variables. In equation j. And Aj is going to be the error term. Okay, so going back, and maybe I need to make this slightly smaller so that you can see everything. So, what we have in this equation, so we have our dependent variable. In equation j, we have our set of exogenous variables, which is that matrix xj. And the set of endogenous variables in equation j is that matrix y capital J. And, beta j and alpha j, these are all coefficients, and not that we go from this equation, from the first equation to the second equation. So what we're doing there is we are combining Cj, so that includes exogenous variables and the vector of endogenous variables within each equation. And delta j is the vector of coefficients related to xj and yj, respectively. Okay, so that's kind of what we did here. So you see, we wrote the equation. So now, we're also going to define a matrix X. X is going to be the matrix of exogenous variables in all the equations. So therefore, the reduced form model for that vector of endogenous variables in equation. J is yj, and that's capital Yj. So it's pi j times x plus uj. Okay, so that is the reduced form model corresponding to all the endogenous variables that we have in equation J. So remember, we're considering just one equation at a time. Okay, so hopefully, with that definition, basically what we're trying to do is, we're trying to write just one of the equations as a function of exogenous variables and endogenous variables. And remember, we're using here y capital J because those are dependent variables in other equations of the system, which for now, we're not interested in analyzing. Okay, so when we're talking about estimators for each equation, they are called limited information estimators. And we're going to be talking about in detail one of the estimators. And then I'll also mention another estimator that's not that popular. So, estimators for, estimators, these things sometimes jump on me. Estimators for each equation are called, some terminology here, are called limited information estimators. Okay, so that's the name. And we're going to be talking about two estimators. And I'm going to call it limited information estimators. Okay, and we'll talk about two. So the first limited information estimator one is going to be just, using IV instrumental variable methods. And more specifically, the one that I'm going to talk about is the two-stage least square procedure. Okay, so again, some intuition, remember, once we write our equation in this form, we go back to the model that we had considered previously when we were talking about just instrumental variables. We have a dependent variable, and then we have, as explanatory variables, a set of variables that are exogenous and another set that are endogenous. So we can just use our two-stage least square procedure. Now, what I'm going to be doing here is I'm going to be writing it exactly in a different way, but it's the same as the one that we had considered before. So the two-stage least square estimator, can be written. So remember, so we have the predicted value of that vector z, so that's inverse, times cj hat times yj, and remember zj include the vector variables that are exogenous and the vector variables that are endogenous, and cj hat is going to include the exogenous variables, and we also have the predicted values of endogenous variables which we obtain in that first stage. So remember, the idea here is that we use OLS for yj equal to pi jx plus uj. Estimate, so that's a reduced form model. That's the first stage of the two-stage regression model. So we estimate pi j and obtain yj hat. Okay? And then the variance for delta j hat two-stage least square estimator is going to be given by sigma jj times Cj hat prime minus 1, and so the sigma jj hat, so that's equal to yj minus zj delta j hat to stage least squares prime times yj delta j hat to stage least squares. So that's the vector of coefficients divided by t. Okay, and remember t is the number of observations. Okay, so now notice that, remember, when we had our discussion of the two-stage least square procedure, what I had mentioned is the fact that if you estimate, you use OLS, and then you get your yj hat, and those are the ones that you use in the second stage, and you just use OLS, the standard errors that you get using OLS are going to be incorrect. Okay, that also applies here. And notice that the way I have defined the variance, where to calculate this variance here, notice I'm using the original zj. I'm not using the zj hat. If you were to use just, like the OLS without doing this adjustment, then you would have a problem. Okay, so this is a different way to write the two-stage least square estimator to the one that we presented before, but actually it's exactly equivalent. However, it's important to present it this way because later on when we look at the estimation of the system, we're going to be kind of relying on this same approach, and it's good to have this procedure in mind. So again, these equations here that I presented here actually are exactly equivalent to what I presented, the matrix form of the remember what I call the one-shot two-stage least square procedure. Let me see if actually I can go back to my notes. That's going to take a while, but I know that I presented it in a slightly different form. That's good for you to remember so that you can compare things. So that's a control function approach. So I'm almost there. Let me see. So actually, yeah, so remember, so this is the formulas for the two-stage least square that that we discussed in class. I mean, we also took the variance, and actually I asked you to derive the variance before. Actually, I had the notation is slightly different because before we call it x prime. Okay, so that approach, so yes, so I have it here. Okay, so remember, that's what we call the one-shot estimator. Well, there's also one way to rewrite this two-stage least estimator, like the way I wrote it today. And for the variance, there is also a way to correct that variance so that in that second stage, the variance is still correct. Okay, but it's basically the same thing. You could also use the formulas that I had given you before and what I call the one shot, and the results should be the same. So, in short, okay, so this is this is the bottom line. You have these simultaneous equation models, but you are only interested in estimating one of the equations. Well, if you are only interested in estimating one of the equations, or you want to estimate one of the equations at a time, you just use instrumental variables. And here, we talk about the two-stage least square procedure, and you follow exactly the same things that we did previously, and and you can do all the tests that we talk about, analyzing the weakness of the instruments, doing the Hausmann tests, and so on and so forth. Exactly the same concepts apply here. Okay, so that's kind of like the bottom line. Okay, so let's look at the limited information estimator number 2, and that's what sometimes is called limited maximum likelihood estimator. Okay, it's not very popular, I have to say. Okay, and the other thing is we haven't talked about yet maximum likelihood estimator. So I'm not going to present the estimator per se, but I just need you to be aware of this estimator because it has some nice properties, and it can be used for sensitivity analysis, and actually it's available in SAS too. And so I mean it's easy to use, but I mean it will take us a long time to cover all the theory. So the first thing is, regarding this estimator, is not very used in practice. Okay, but it's mentioned in the literature. Of course, it has some properties, as every estimator, so there are some advantages and disadvantages. So the advantage is that it's robust to weak instruments. Which, remember, that's a problem. But the catch here is that it requires a normality assumption. So it requires normality of the errors, which might be satisfied in some cases. It might not be satisfied in other cases. Okay, so that's the catch there. And the idea here, you use that estimator that's used mainly for sensitivity analysis. Sensitivity analysis for two-stage least square. If the results are very different, that can be seen as evidence of a weak instrument problem. If results are very different, that can be seen as evidence of a weak instrument problem. So again, so this is called limited information maximum likelihood estimators, not very used in practice. It's robust to weak instruments, but it requires the normality of the errors. So you can use for sensitivity analysis, especially in the case where your instruments, in some cases, there might be borderline weak. So you do those tests and kind of find some evidence that those instruments are kind of weak. Then you can use this one to see if that really matters. Okay, but of course you will need that normality assumption. Okay, so in practice, to be honest with you, two-stage least square in instrumental variables is the estimator of choice. But it's good to have in mind. I mean, it's also good that you know something about this estimator. Okay, so we're done with these limited information estimators. So now let's look at the system methods of estimation. So system methods of estimation. Now, and because we're estimating all of the equations simultaneously, sometimes these estimators are also called full information estimators, of course, to differentiate them from these limited information estimators. So these are the full information estimators. Okay, so we have to write it in a similar way to the way we wrote SUR as a generalized linear model. So we're going to do again the same thing, and we're going to rely on the notation that we use to denote each individual equation. So remember now what we have, we're going to have a vector t by 1 of dependent variables, and we're generalize it to the case where we have m equations. And then the way to write this is going to be very similar to the way that we wrote it again, the SUR as a generalized linear regression model. So we have in this kind of diagonal matrices, we have the vector of explanatory variables for each of the equations, and then we have zeros elsewhere, so this is a big matrix. Okay, so here we will have our vector of coefficients for each of those equations. So we have m equations, and then here we have our error terms. Okay, so in a way, again, we wrote it using kind of the same notation that we were using before for SUR. So just to remind you in terms of observation, so this is going to be mt by 1. So here this is going to be mt times the sum of those kj's. We're assuming that each equation can have a different number of explanatory variables. This is going to be the sum of the kj's times 1, and this is going to be mt times 1. Okay, again, so here, just as a side note to remind you that the way that we wrote each equation was yj equal to xj beta j plus capital Xj alpha j plus ej, and then we put together xj and that capital yj. Okay, so this is what we're using. So we're using this second equation. That's what we use to write that. Okay, so now what we're going to be doing is we're going to be using changing notation to denote the whole vector. So we're going to be calling y tilde. So that includes, that's all that vector. It's going to be equal to z tilde, which includes all that vector, delta tilde, is that vector, plus e tilde, which includes that vector. Okay, so again, in terms of our assumptions, so this is again the exogeneity of the exogenous explanatory variables. Okay, and we also have our omega matrix that satisfy, remember this, the SUR assumption. Okay, so kind of two things going on here in this system. So first of all, you can see that this just looks like an SUR system, the SUR system that we had before. But the problem here, is that we also have endogeneity. Okay, because remember, here within those Z matrices, we have these yj's, which are endogenous variables. Okay, so one way to think about simultaneous equation models, or another way to think about the simultaneous equation models, is like a similar related regression model where we have endogeneity. Okay, so we need to account for the issues related to both endogeneity and also to a simultaneous equation model where we're trying to devise an estimator for the coefficients. So to address endogeneity, to address these two issues, the issue of endogeneity and also the structure of that omega, which, remember, that corresponds to a generalized linear regression model, generalized regression model, then we can use what's called the three-stage least square estimator. So to address endogeneity, and the structure of omega, we can use what's called the three-stage least squares estimator. Okay, so this is three-stage least square estimator. Okay, so how that estimator works? So we have this delta three-stage least squares. Remember that delta, well, it's that big, so here I guess I need to be a little bit careful. So it's going to be that delta tilde hat, because that's what we're estimating. It's going to be equal to z tilde hat prime times omega inverse. So this is the Kronecker product times z inverse z tilde hat prime omega hat inverse Kronecker product and times y tilde. Okay, and the variance of this delta tilde hat three-stage least square estimator z tilde prime hat omega inverse inverse, which, if you remember, that looks very similar to the structure of the feasible SUR estimator, or feasible generalized least square estimator, apply in the context of SUR. Okay, so how does the procedure work in practice? So that formula looks pretty simple, but let's see how. Remember, we call it three-stage least square, so there are some stages involved in the estimation of these matrices. Okay, so let's look at the procedure in detail. So how does the procedure work? Okay, so first, we need to estimate that vector of pi j by OLS and compute. So we need to compute those reduced form models for yj hat, for each equation. Okay, so yj is going to be equal to pj times x plus uj. So remember, these are the reduced form model. For each vector of endogenous variables in each equation. Now, let me finish with that. So, we need to estimate these reduced form models for all of the endogenous explanatory variables that we have in each equation. And once we have that, we can generate the matrix of Cj hat. Remember, so that is to be able to apply, this matrix we use when we're talking about the two-stage least square procedure. So we use the predicted values of that first stage. Okay. So that's the first stage. So in the second stage, so once we have that, we can use now our two-stage estimator. So we'll compute delta j hat two-stage least square, zeta j hat prime, zeta j hat minus 1, zeta j hat prime with j. So basically what we're doing here, you see, one way to think about it is that we're using two-stage least square for each of the equations. Okay, so that's what we're doing here. So once we have that for all of the equations, we can estimate the variance, covariance matrix for the equations in a similar way in which we do it for the SUR. Zi delta hat two-stage least squares prime. So these are the errors of the I equation times the errors of the J equation. Okay, divided by T to form our sigma hat matrix. Again, a similar way in which we did it for SUR. So this is the matrix of correlations between the errors. And so on and so forth. So it should be 1m. I'm writing too fast. Okay. So again, kind of, to summarize, what we do is basically, we use two-stage least squares for each of the equations. Once we have errors for that two-stage least squares, we for this omega matrix to calculate the covariance matrix of the errors for all of the equations. Now, something that I wanted to mention, and again, I think that I'm gonna thinking twice. Let's continue, and then I'll go back to detail. And once we have that, we can compute. Oops, what happened? Yeah, happened. Took me to the end. I don't know what I touched, but it took me to the end of the document. I'm saving it, so give me a second before I lose any information. Okay, so once we have all that information, we can compute. We can use the formulas I already give you for the three-stage least square estimator. So 3, we can compute delta 3, delta. How did I call that? Let me see, just so I'm trying to be consistent. 3 SLS, okay, without any comma. So we can compute that delta tilde hat three-stage least squares and the variance of that delta tilde hat three-stage least square estimators using the formulas above. So again, basically what we're doing here is we're using two-stage least squares for each equation. with the errors from the two-stage least squares results, we're able to calculate the correlations, and once we have the correlations, we can construct this big matrix Z, okay, with the Z hats, and we can apply this formula for this three-stage least square estimator. Okay, so it's actually very, the procedure, once you understand what's going on, is very straightforward. So what are the properties? Since, we always talk about the properties. Properties of three-stage least squares if the assumptions are satisfied. So the first assumption is going to be consistency. And the second assumption is going to be asymptotic efficiency. Okay, so not here. Here the emphasis, it's the same thing as the emphasis with two-stage least squares. So remember, the emphasis is in long, very large sample properties. Okay, so no, but this is a question that is worth thinking about. So remember, we talk about, we're trying to estimate this system of equations. So one way to go about doing it would be to estimate each equation separately, if that's possible, or we can apply our system of equations. So we estimate each equation, the coefficients of each equation separately. We have this limited information estimator, and we estimate them together. We use this simultaneous equation estimator. So what do we gain? Consistency, we're going to have in both cases for both limited information estimators and also full information estimators. But asymptotic efficiency, again, if all the assumptions are satisfied, we will only have in the full information estimators. Okay, but you have to be a little bit careful. So and that's what, I'm going to posit this question. Are system estimators or full information estimators always better than limited information estimators? Okay, so if I were in class, I would ask you that question, and I'll have you thinking about it for a couple of seconds. We'll have a discussion. Since we cannot have that discussion, I'm going to have to give you the answer, and the answer is no. But then why? Well, one way to think about it is that, the problem with estimating a system of equations is that you are assuming that all of the equations are correctly specified. Okay? So, and that might not be always the case. So, it's possible that one equation is correctly specified and the others are not correctly specified. So the errors kind of propagate through the equation. And that's kind of like the risk, one of the risks of estimating this, system of equations. So the idea here is that a specification errors in one equation can get propagated to the entire system. Okay, so that's kind of like a risk that you are running. So you see, the advantage then of using limited information estimators are that they contain the problems within each equation. You are not propagating the errors. So contain problems within each equation. Okay, so also another advantage is that these limited information estimators are easier to estimate. Okay, and remember we're talking about asymptotic properties, and actually in small samples it is possible, but the thing is you don't know that limited information estimators are more efficient than feasible, that full information estimators. Okay, so you need to be aware of that. So in small samples, what has been found it is possible that limited information estimators are more efficient than full information estimators. Okay, so have in mind, even though we have this what's called full information estimator, that doesn't mean that it's always are going to be better. So, what do we do in practice? Well, it depends on the specific application that you have at hand. Sometimes you're just interested in one of the questions, so you can estimate the limited information estimator. There might be some reason for why, you might gain some efficiencies. You run just one of the questions separately and nothing is significant. So you say, okay, I'm going to estimate the system of equations to see if that allows me to gain some efficiency. So in that case, you can use, you can try to use the system to see if you really get any gain on efficiency, and hopefully the results also don't change much. You can always use these different estimators as robustness tests. In other cases, you will see in the context of systems of equations, sometimes you have endogeneity there. So, you have to estimate it as a system because that's what you need to do. If you, for example, you are estimating a system of demand equations, sorry, I forgot to mention that. You have to estimate it as a system. So that's the model that you have to be estimating. Okay? So anyhow, so that's kind of what I have for you today, kind of as a general summary. So today we talk about estimations of these simultaneous equation models, and we talk about two options. So we can estimate each equation separately using limited information estimators, and usually the estimator of choice is the two-stage least square estimator. And then to estimate the system as a whole, as the entire system, all the equations simultaneously, we can use what's called the three-stage least square estimator, which, if you want to think intuitively, is basically a combination of instrumental variables procedures and SUR procedures. As a matter of fact, in the first stages, you run two-stage least squares, and then in the second stage, so in the first stage, you run like a reduced form model, for each equation. Second stage is two-stage least squares for each of the equations in the system, and then the third stage, you use like generalized regression model where you account for the correlation across equations.